I'll just switch over to your slides.
I saw that. That was a great montage.
Yeah, all the photos are the ones that were collected by tomorrow.
Mhm.
Yeah, I should say that actually.
Right. Get the microphone? Yeah. Get on.
Okay. Laser pointer. Okay, great. Thank you.
So let me just mention that the photos showing between the talks, those were collected by Tamara Servi by many friends of Zoe. And our next speaker is Dave Marker, who will speak about rigid differentially closed fields.
Thank you. It's always a great pleasure for me to be back at Fields, and it's particularly a great pleasure to talk in honor of Zoe. So Zoe and I think both first came to Fields in when there was a special year in 1996-97, and I mean the last time we met in person was in Fields in 2021. So I first met Zoe in 1980 when she started graduate school at Yale, where she and I were both students of Angus MacIntyre. I mean, this sounds like a long time ago, but I realized in preparing this talk that both Francoise and Anand have known her even longer. Zoe also always referred to that period at Yale, as Francois said, was really very exciting. Angus had attracted a great number of really interesting visitors around him, and Zoe often referred to this as sort of the best part of her, the best 3 or 4 years of her life. Something I often agreed with, though my wife never liked it when I said that. So, I mean, we developed a close bond, and in many ways, Zoe was like a sister to me. And even though I'd started graduate school a little bit earlier, she was much more mature mathematically and knew the logic community much better than I did. So she was a sort of guide for me. I particularly remember my first trip to Europe for the Logic Colloquium in 1981 at Marseille, where basically she took me under her wing and guided me throughout how to get around Europe, how to deal with people at a big conference. It was really a great time. As I said, in many ways, she was like a big sister. And like with family, things weren't always smooth. I can think of at least 3 times I swore I would never serve on an organizing committee with her again. And I could never shake the feeling she was vaguely disappointed in me. But I knew she would always have my back and do anything for me. I mean, she was a generous friend. I mean, she always had people staying with her, and she really enjoyed taking care of people. And it was always a great joy when she was delighted in something, whether it be a piece of math or food or a movie or dancing, which would always please her. I want to tell a couple of brief stories about just sort of illustrating the way Zoe took passions. This is one that it's really short-lived, but when she was a postdoc at Princeton in the late 80s, she became a fanatical baseball fan. In particular, she was a fan of the New York Mets. I mean, she started in about 83 when the Mets were not so good, but by 1986, they won the World Series, which was really fantastic. And they won the World Series in Game 7. They were behind going into the 9th inning and came back in the 9th inning to win. And Zoe had videotapes of the game, which she watched the series starting at the beginning very, very often. I remember calling her once, and her boyfriend Peter told me it wasn't a good time to talk to her because it was in Game 7 and the Mets were still losing. I mean, there was another time around that same period. I visited Paris in December, and she would go out first thing in the morning The excuse was to get us bread or croissants, but in reality, what she wanted was the International Herald Tribune, so she could read the sports section, because this was the time when baseball trades were happening. Yeah, unfortunately, her passion with baseball didn't last once she moved back to Paris permanently. So we've mentioned a lot of her mathematics here. Of course, she had these major contributions to the model theory of difference fields, which is, that's where a lot of the connection to dynamics comes from, but also her work, some of my favorite work was her work on pseudo-finite fields and field arithmetic. She also did important work in pure mathematics and pure model theory. But she also did great service to the model theory community. I mean, she managed several large European grants. She organized special sessions at Newton and Poincaré Institute. And she really was known for her making a major effort to make students and young researchers comfortable in the logic community. And often putting them up in her house and making sure that they always went out to beer with us and were always invited to speak. She'll be profoundly missed professionally, but I think all of us who knew her will miss her very much as a friend. Okay. Another quick thing is that whenever I post a preprint on arXiv, almost certainly the first comments on it I got were from Zoe, and which is the case for the thing I'm talking about today. Okay. So this starts with a sort of basic question that we might have wondered about before. It was asked to me by Russell Miller. Does every differentially closed field have a non-trivial automorphism? So in the model theory of differential fields, at the beginning of the subject, the theme was that differentially closed fields behave a lot like algebraically closed fields. I mean, that later changed where now it's that differentially closed fields behave nothing like algebraically closed fields, and that's become really interesting. But of course, so I call a structure with no automorphisms rigid. If you ask the same question for algebraically closed fields, if I start with an algebraic closed field of size kappa, it has 2 to the kappa automorphisms easily. And we studied differential automorphisms a lot in differential Galois theory, but somehow this question had never been posed. And the theorem I'm going to talk about today is there are rigid differentially closed fields, and in particular, there are countable rigid differentially closed fields, which was Miller's question. I'll say a word about Miller's motivation, because it seems like he was actually asking the wrong question. He wanted to show sort of a generalized notion of bi-interpretability. And the question was whether countable graphs, there was some way of taking countable graphs, assigning to a countable graph a differentially closed field. There is, and it's an important idea to do that, but he wanted to do it in a way that this sort of bi-interpretability condition that when you do this, you don't introduce new automorphisms. So since there are graphs with no automorphisms, you would need to know there's a real differentially closed field with no automorphisms. He believed that wasn't possible. So when I showed that there are rigid differentially closed fields, that shows there's no such functor, but there's a much easier argument for, So because there are rigid real closed fields, rigid graphs aren't a counterexample to what he wanted, but it's sort of very simple. And if you take a graph which has an automorphism of order at most 2, of order bigger than 2, you could never have even an algebraically closed field that has an automorphism of order greater than 2 by Ert and Schreier theory. So it's impossible even for the underlying algebraically closed field. So it's certainly impossible for the differentially closed field. So we've sort of dismissed this without going through my work, but I think it's an interesting question to begin with. Okay, I'm going to talk about preliminaries. I'm going to define a lot of things, probably a lot of things I'll say too quickly. Please feel free to interrupt me. Okay, so I'm only going to talk about fields of characteristic 0. a derivation. It's the obvious thing. And DCF is the theory of existentially closed differentially closed the theory of existentially closed differential fields. So these are differential fields where you can solve as many equations as possible. So if I have a system of algebraic differential equations, infinitely many variables, and there's some differential extension field in which I can solve these equations, then there's already a solution in K. So that's the definition of a differentially closed field. So if I talk just about polynomials, this would be one way of defining an algebraically closed field. It's not a great way because it talks about, it's not restricted to just the field itself. It's also talking about all extensions of the field. Now, from a logical point of view, you'd rather have a way where you just talk about K. And a lot of this comes out in the work of Bloom, although I attribute to her some things that are really due to Robinson as well. But you can axiomatize this theory. It's omega stable. You don't need to know what that means. I'll talk about consequences of it. But a key thing is that it has quantifier elimination. What this means is that, in logic, we talk about things where you're allowed existential and universal quantifiers. And in differentially closed fields, you don't need them. All you need to do is to talk about things that have no quantifiers. And what can you say with no quantifiers? You can say that certain polynomials vanish and certain polynomials don't vanish. So definable sets are just sort of finite Boolean combinations of differential algebraic varieties. Okay. So this was the starting point, and this is this is the differentially closed fields are a lot like algebraic closed fields. Where the model theory really paid off at the beginning was in showing that there's a notion of differential closure. So if I start with a differential field little k, we say that an extension is a differential closure if it's differentially closed and has the property that if I take any other differentially closed extension, then I can embed K into L. In model theoretic terms, the differential closures are the prime model extensions of differential fields. Okay. And now the theorems, which rely heavily on the omega stability, which say is at first every differential field has a differential closure. That followed just from the omega stability and some old work of Morley's. Shalaw's contribution was that saying if you have two differential closures, then they're actually isomorphic over K. And a condition we're going to use is that if K is the differential closure, then any element of K to the n is atomic over K. What that means is that if I take an element of take a tuple in the big model, I can write down one formula which sort of describes its behavior over the small model. In particular, if I have two elements that satisfy this formula, then I can find some big superfield with an automorphism moving one to the other. Okay. And this followed out of Bloom's work plus older work of Morley's. Okay. So this work leads you to the following idea, which I think is almost makes you conclude there have to be automorphisms. If I start with a differentially closed field K, and it's the differential closure of a proper subfield, and I take any element of the big field that's not in the small field, I can find an automorphism that moves it. And this again is this is where Zoe's comments came in. She sort of streamlined the art. I went sort of back to Shalaw's proof to prove this. And she pointed out some other arguments that did this. Okay. Well, I know this element there's a formula that isolates this type. Because the small field is definably closed, it can't be the only thing satisfying this type. There has to be something else, otherwise it would be definable. So these things have the same type, so I can find an isomorphism between the differential fields they generate that fixes little k. Now again, coming out of the basic theory, I can argue that big K is not really a differential closure of little k, it's a differential closure of the things when I add a finite tuple to it. And then by the uniqueness of differential closures, I can find, I can extend sigma 0 to an automorphism of k. Oh, sorry. That's the whole proof. Okay. So if I start with a differential field, I extend it to its I take a proper extension to its differential closure, then I get an automorphism. Well, why doesn't this tell me they're always automorphisms? Well, the first question is this always true? If I take a differentially closed field, is it the differential closure of a proper subfield? So ultimately, I'm going to claim the answer is no, because I construct a rigid thing, and that isn't the case here. The second, well, I built this automorphism by general nonsense. I mean, there has to be more than one, right? But again, the answer is no. And this goes back to Michael Singer's work. He introduced the idea of closed ordered differential fields, where you look at the existential closure not just of differential fields, but of ordered differential fields. And one of his theorems is that if you take a closed ordered differential field and you adjoin a square root of -1, that gets you the differential closure. But the only automorphism of the differential closure over the closed order differential field is just conjugation. So it's possible that if when I look at a pair of a differential field and its differential closure, it's possible there are only two automorphisms. Pardon? Right. Yes, this should be K. It should be F. Thank you. So this comes back to a remark Omar made to me, and a question he had thought about is, take a differentially closed field. Is there always a closed order differential field that it's an extension of? So again, the analogous theorem in just the algebraic case is, if I have an algebraic closed field of characteristic 0, I can always find a real closed field such that if I join I get the algebraic closed field. And it always has a codegree 2 subfield. In fact, it has continuum many, or it has the maximum number. But does every differential field have this property? And again, if we construct a rigid one, the answer is going to be no to every question I asked. Okay, let's go back to preliminaries. We've talked several times this week about strongly minimal sets. I also want to talk about the notion of model theoretic algebraic closure, which I'll just call closure to try and not confuse things. But in differentially closed fields, it's a sort of clear algebraic notion. If I have a set B and I want to take its closure, I just take the differential field it generates and take the algebraic closure, the field theoretic algebraic closure of that. So this is the notion of closure, and it'll give us a notion of independence. Okay, and then the notion of strong minimality. Again, assuming I'm in a large enough field, saying a set is strongly minimal, it's a definable set that I can't partition into two infinite definable sets. Okay, because of quantifier elimination, in this case, you can think of it, if the X is a differential algebraic variety, this is equivalent to having no proper infinite differential subvarieties. Okay, so the simplest example of a strongly minimal set is the constant field. Okay. And one of the consequences of stability is that I take the constant field that's sitting inside this big differential field, but the big differential field gives no extra structure on it. So if I take a big set X, and X could be defined using derivations, it could be defined using parameters from the big field, when I intersect it with the constants, I get something that I could already define in the constants alone, just as a field. And this is an example of this is one example of the strongly minimal set. And we'll look at a couple of others today. I mean, this is understanding the strongly minimal sets is now one of the major themes in differential algebra. And things that come up in Ronnie's talk and Ronnie and Jim's work, a lot of the work of Remy and our joint paper. Okay, independence just means independence with respect to this closure operation I've said that. So a set's independent over little k. If I take one element out of the set and take the closure of what's left, I don't get any. I don't get that element back. And the dimension of a strongly minimal set is the maximum size of the size of a maximum independent set. There's also the notion of one or two strongly minimal sets really different, and this is the notion of orthogonality. Technically, it means that there's no definable finite to finite relation between the two sets. The practical version of this that I'm going to use today is that two strongly minimal sets are orthogonal. Is if I add an element to one and take the differential closure, it won't add any elements to the other one. Okay. So how am I going to build something rigid? I'm going to take what I consider a really stupid strategy. So I want to build, k countable. So take an element of k, let's say that's non-zero. I want to associate to it a natural number, which is a dimension of something, such that this is an isomorphism invariant. And that it's one-to-one. Okay, if I could do that, so I've associated every element of field a number. It's invariant under isomorphism, and this is I've associated a unique number each thing. Well, then I can't have any automorphisms in the field. Okay, so that's the rough idea. Pardon? Yeah, yeah, it's an automorphism. Well, I mean, yeah, let's say it's an automorphism. Yeah. Okay. So I need a way to do this. And these numbers are going to be, essentially what I'm going to do is to each element of the structure, I'm going to associate a strongly minimal set. And this number will be the dimension of the strongly minimal set. Okay. So the first try at this goes back to work of Rosenlicht. I let f of x be the function x over 1 plus x. I mean, his arguments work for a lot of things, but this is sort of a very simple version of this. And I look at the differential equation, just the derivative of x is a f of x. These sets are strongly minimal just because they're order 1. And Rosenlicht, if I varied f over various rational functions, Rosenlicht had a classification for when these are non-orthogonal, to the constant, so very closely related to the constants, and when they're not. And it has to do with the partial fraction decomposition of the function f. But these, for this particular function f, these are all going to be, very different from the constants. And what he really showed was that they're very different from each other. So first of all, If I add a new element from one of these sets, I don't add any new constants. And then this condition, if I have two elements, one is in one of these sets, one of them is in the other, and they're algebraically dependent over K, then either each of these points is already algebraic over K, which is a trivial case, or they're equal, which is even more trivial case. So basically, if I take two of these sets and two different elements, they're going to be independent. And Rosenleich used this to prove one of the first results about how differentially closed fields are very different from algebraic closed fields, in that if I start with a field, I take its differential closure, it's possible there's a isomorphic copy inside, so that the differential closure isn't necessarily minimal. I take A and B, just non-zero. I take the two Rosenleich sets, take a pick point from one and a point from the other. Basically, the only way they can be algebraically dependent over K is if they're already in K, algebraic over K, or they're equal. So, I mean, so you may be confused because how could they be equal if A is not, but I'm allowing the case that A equals B. I'll say that in a second. What? It's possible that A, I'm not saying A is not equal to B, and we'll use that, in fact. So what this says in model direct terms is that I'm orthogonal to these sets are orthogonal to the constants. If A is not equal to B, they're orthogonal to each other. And if A equals B, XA is basically a set of independent elements. Okay. So now I'm going to use these sets to build a rigid field. Now, the problem with the Rosenleich sets is, for these sets, the dimension is always infinite. I can't get sort of natural numbers dimension, so I'm going to get give up trying, for the moment, just as a warm-up, I'm going to give up trying to associate natural numbers and instead try and associate cardinals, infinite cardinals. But I need there to be enough infinite cardinals. So I'm going to make a, so this is, again, a toy version of the argument. I'm going to assume I have a cardinal kappa, where kappa is the kappath cardinal. So there are kappa cardinals below them. I mean, you start with any cardinal lambda and take lambda n plus 1 to be aleph sub lambda n. Then you take lambda be the limit of the lambda n's. That will be a cardinal with this property. So from the point of view of real mathematics or even model theory, these are very large. I mean, although these are not large in the sense of, these are not what set theorists think of as large. Okay, but here's a case where I have lots of cardinals. Okay, and so this will give me that there are arbitrary large rigid models, and it'll answer the two questions I had at the beginning, that there are differential fields which aren't differential closures of proper subfields, and which aren't differential closures of models of Singer's theory. Okay, so here's the case. I'm going to build a chain of alpha models where the alpha model in the chain is going to have size aleph alpha, where alpha is less than kappa. And we also build an injection listing all of the elements of K alpha. And if alpha is, and at limit stages, I take unions, and at the end, I take the union of all these things, and that'll get me something of size kappa. And what I do at stage alpha plus 1 is I look at the Rosenleich set that corresponds to A alpha, and I add Aleph alpha plus 1 elements to this set. That's all I do, and I take the differential closure. So I make sure that this set at this point has dimension alpha plus 1, Aleph alpha plus 1. Now, pardon? A alpha will be in K, A alpha will be in K alpha. It will be some element of K alpha that I haven't used yet. So I have some bookkeeping to make this list. And I want to eventually list everything. So this set is orthogonal to the constants, so I add no constants as I go through this. For alpha less than beta, these sets are orthogonal. So at later stages, when I add new elements, it won't add any elements to this set XA alpha. So the set XA alpha at every stage will only have size Aleph alpha plus 1. Okay. So in particular, when I'm done, if I take an alpha that's not beta, then the set XA alpha and the set XA beta will have different cardinalities. So no automorphism could map A alpha to A beta, so these are rigid. Again, I mean, okay, this is a toy example because and the problem was I only had infinite cardinality. I had to, in the Rosenleich sets, which are ones I understand quite well, so my first choice thing to look at, I don't have the choice of having finite dimensions. I need something where there are finite dimensions. Okay. So the above argument only worked because we had kappa choices of dimensions for strongly minimal sets. I need to be able to assign finite dimensions. Okay, so I'm going to give you, again, my other favorite examples of strongly minimal sets that I thought about for many years. These are Monin kernels. So I'm going to start with an elliptic curve. Now, working in the differentially closed field, so the differentially closed field is sort of an infinite dimensional object. So the constant field is sort of, think of the constant field as dimension 1. The constant field squared, which is isomorphic to the solutions to x prime equals 0, would be dimension 2. You can think of vector spaces over the constants have dimension n, and all of these things can be thought of living inside of K. So K is sort of infinite dimensional. So this is an infinite dimensional object from the point of view of the differential field. What Monin did in later Boehm was you look at the torsion points of the elliptic curve, and you take its closure in the Colchin topology. So the smallest Colchin closed set, subset of this differential algebraic group, that contains the torsion. And if I did this with where A was a constant, this would just be the constant points of the elliptic curve. But if A is not a constant, this becomes interesting, and it solves a second order nonlinear differential equation. And similar things can be done for any abelian variety. So, as I said, these come up in Monin's proof of the Mordell conjecture for function fields. And these were later studied by Alex Boehm. And from the model theoretic point of view, which I think really sharpened what's going on here, by Hrshovsky and Sokolovich in what I think is the most important unpublished paper in model theory. I mean, this is so I think it was accepted for publication, but never actually revised. Okay, so one of the results, so first of all, is this Monin kernel is a strongly minimal set. And it's orthogonal to the constants, and it'll be orthogonal to all of these Rosenleich sets. It's non-trivial in the sense of where Ronnie was talking about geometrically trivial. This is an example that's non-trivial, but also not the constants. And it's sort of one of the big results of their paper is that there's a trichotomy that either in differentially closed fields, either non-orthogonal to the constants, you're non-orthogonal to a mononkernel, or you're trivial. So a lot of what we're doing now in the subject now is trying to understand the trivial, which yeah, so it's, yes, right. It's necessarily a subgroup, yes. It's sort of the, it's also sort of the, it's the minimal differentially closed subgroup, infinite differentially closed subgroup. Okay. Okay. Okay, these can have finite dimensions, and that you can make them any dimension from 0 to whatever cardinal you want. Also, we have a complete understanding of what non-orthogonality between mononkernels is. The only way you get non-orthogonality, so the only way these can be intimately related, is if the elliptic curves are isogenous to begin with. So there's a finite to one algebraic homomorphism between the curves. What we'll use frequently today in this argument is that if I have A and B, which are algebraically independent over Q, the curves are non-isogenous, so the curves are non-isogenous, so the mononkernels are orthogonal. Okay. So again, I want to show there's a countable differential, rigid differentially closed field. You could say, okay, well, you just assign a different dimension to each mononkernel. Well, that can't work. In part, if A is constant, the mononkernel is just the constant points of the elliptic curve. So there's nothing to, you can't differentiate those by dimensions. Also, you have the property that if the elliptic curves given by A and B are isogynous, then I have to have the same dimensions of the mononkernels. So I'm going to look at something else again. So I basically took my two favorite things and put them together. So what I'm going to do for each A is I'm going to take the Rosenlich set, and I'm going to look at the dimension of the mononkernels for things in that set, and I'm going to ensure it has a maximum, and the maximum is going to be NA. And for A not equal to B, I'm going to make these NAs and NBs different. So that would give me a way, some automorphism invariant that distinguishes each point in the field. Of course, 0 I don't have to worry about, but that would give me a construction of a rigid thing. So as in the previous argument, we just sort of do it. I'm going to build a countable extension. As I go, I'm going to come up with some kind of enumeration of that extension. And I'm going to build an increasing sequence of natural numbers so that, well, so all of these fields are differentially closed. All the constants that come in at the first step. If I look at the Rosenlich set associated with AI, sort of as in the previous example, all the elements come into it by stage I+1. So I won't add, I may add an element to that at stage I, going from I to I+1, but I'll never add an element later. It'll also be the case that if I take a B that's in XAI, I may add a point to it in KI+1, but I'll never add points to it later. And finally, I'm going to have to make sure that NI+1 is the maximum for this. Okay, if we can do this, then we can guarantee that there are no automorphisms of K. So I start with a differential closure of Q. At stage S, I choose a new AS and KS. And now what I'm going to do is I'm just going to add a new element to the Rosenlich set associated with AS. And again, that will be independent from everything I've done before. And now what I'm going to do is I have ns minus 1, I'm going to add more than that, independent realizations to the mononkernel of the elliptic curve associated with BS. Okay. That's a generic point over the field I've got so far. And I let my ks plus 1 be this new element of the Rosenleich set plus ns plus minus 1 plus 1 new independent realizations. Okay, so what happened? Okay, I'm adding elements to a Rosenleich set. I'm adding independent elements of the mononkernel, so I never add new constants. As I go on, I'm always adding elements that are in strong liminal sets that are orthogonal to the ones I'm caring about. So I'm never going to add new elements to the specific Rosenleich set or mononkernel that I worried about before. The last requirement is a little bit more subtle, but not much. Essentially, what it shows is that if I take a non-zero element in the ith field, and I look at how many independent elements are in that Rosenleich kernel, it's never going to be more than one of the bounds I'd come up with earlier in the construction. And again, this isn't so hard to show. And I'm not sure why I wrote it this way. I think in all of this construction, you can always take nj to be j, I think. There's no reason to why this is their actual jumps here. Somehow, at one point, I thought something more subtle could be going on. But basically, at this stage, no mononkernel has size bigger than ns minus ni minus 1. So when I add more elements at this stage, I'll have made sure that the maximum at this stage is bigger than anything before, and I won't change anything before because I'm adding something that's orthogonal to everything that came before. Okay, so I mean, it takes a little bit of thinking to make sure this works, and a little bit of computation to make sure this lemma works. But basically, if we look at the Rosenleich sets we care about and the mononkernels we care about, we add points to them at some point. We may have added a few points before, but we never add any points afterwards. Okay. And that's enough to finish this construction. A couple of bells and whistles.
So you have this chain of KIs. So each one of those is the differential closure of something. So it has automotive, right? So each of them.
Yes. Yes.
So then, is there a geometric way to picture why that if you take one of those automorphisms, why it doesn't extend to the next one?
I mean, essentially because I'm adding things so that dimensions don't work out. So there's no way to map. I'm adding, sort of, I may have an automorphism that moves something to something else, but the associated thing, the things associated with them. So I mean, at the beginning, I may have two elements, and so in the mononkernels for the Rosenleich sets associated with those, they all have dimension 0. Okay, that'll be a base case. Now, what I'll do is I'll take one of those elements, add something to that Rosenleich set, and for that elliptic curve, I'll make the dimension bigger. For the other one, I didn't. So I can't. So I'm killing the automorphism that way. So I mean, this is vague, but I think that's sort of the idea. Okay. Oh no, wait. Okay. So having build one, you can build continuum many. So I mean, there was a long embarrassing period of the subject where, because of general work of Shallah, we knew that there were either countably many countable differentially closed fields or continuum many. It couldn't be in between. And so a major open problem in although the mononkernel ideas end up being crucial to Rorschachsky's work on the Mordell-Lang conjecture. So I mean, sort of the payoff was much bigger than the goal at the time. But their idea, and it's a variant of this is in a paper of Russell Miller and myself, is basically you can sort of code graphs into differentially closed fields. I'm going to basically take the Rosenli set X1 and take any graph you want on X1. And then what I'm going to do is I'm going to add points to the mononkernel of E of A plus B, where this is just addition in the field, if there's an edge between A and B, and I won't if there's not. And again, by the orthogonality conditions, we have a choice of doing this freely. So when I look at the differential closure of what I build, so here I should take differential closure. In this field, if I want to know whether there's an edge between A and B, I just look at the dimension of the associated mononkernel, and that'll tell me, and that's an invariant of the graph, and an isomorphism invariant of the structure. So it'll code the graph in. And this is how Rorschach, roughly, this is sort of a Schla idea, of course, but it's this is the coding. I mean, they basically use the fact that if you have E and I dop, you have many models, but basically this is reason why in this case. And so I can then starting with this field that codes the graph, I basically do the other construction freely on top of it, and then I will get I'll get a rigid model that still codes the graph, because I won't be adding points to these strongly minimal, to these mononkernels, so this will still code the graph. Some questions, and this goes back to things that I think maybe Omar asked and Michael Singer is, okay, I showed there can't be one out. I showed there can be just one automorphism. Can there be just two? So if that were the case, the field would be take a model of closed order differential fields and a join I. I'd need to have that the model of CODF was rigid, and I need to know that every automorphism big K fixes F, but I have no idea to do that. Second, I mean, this sort of strategy seems really sort of naive and stupid, and it should be much easier to do this. Usually, if you're trying to build a rigid thing, it's much easier in Aleph 1 than anything else. But in Aleph 1, I only have countably many cardinals to work with, so I can't do this construction in Aleph 1. Can you do this here or do it in any other cardinal? Again, you need to do something more subtle. You need to somehow code graphs or something in a much more subtle way, and I'd be very curious to see that. So thank you.
Questions for Dave?